Okay, in this last video for today, what we're going to do is try to see how all three little Green's theorem functions will come into play when we try to do something 3D. Now, the easiest thing that we can do that's 3D, but is not 2D, is to draw a little tetrahedron. So what I'm going to do is draw something that looks like coordinate planes here. I'm labeling this X, but all it has to do is be parallel to the X-axis. Same with Y, same with Z. I want to draw a tetrahedron. Remember, this just looks like the graph of the planes we were drawing earlier in the semester. We need a curve C, and for a curve C, what I want is just a boundary of the front face. So boundary, it's in the shape of a triangle. It's like this. I'm going to call T the front triangle. So this is actually going to have area. And I want to label the other triangles. I'm going to label the bottom one, since it's perpendicular to K, so the bottom triangle, I'm going to label T3. The triangle on the left, the left triangle, I'm going to call T2 because it's perpendicular to J, and the back triangle I'm going to call T1 because it's perpendicular to K. So what I want to do is to find the work done along this front face, and then we're not going to do that. What we're going to do is find the work done along the bottom triangle. So that's going to go work like this, and like this. And then I'm going to do the work done along the back triangle. Well, that's going to do this, and this, and this. And then I'm going to do the left triangle. And this is all counterclockwise. So I'm going to go like this, and like this. And you can see that when we add up all the work done of all those triangles, the back work done along that back edge is gone, because we did it one way and then we did the other way and it canceled. Same with this left edge, same with this back edge down here. So if I add the work done from those three pieces, what I actually get is the work done on the front. So let's write that down as a conclusion. The work done on the front triangle is actually the sum of three. How about if I call this, C1 will be the back triangle, but just a boundary. C2 will be the left side, but just a triangle because we're just doing work here. Plus C3 is going to be the boundary of T3, which is the bottom. Now, why is this an advantage? Well, it's kind of weird. Remember, this is a teeny tiny tetrahedron. It's the only way this does us any good. If I look at, let's look at C3 first. What is that? That's the work done along a teeny tiny triangle by a vector field. Now, the vector field does have three pieces. It does have F1i plus F2j plus F3k. But if I'm doing work just along C3, which is the bottom, that's perpendicular to K, so the K part is not going to do any work. So all we're actually getting is basically the Green's theorem thing, because it's just basically in the xy plane. The only thing that's actually doing any work is F1, F2. And so I should put the integral here that corresponds to Green's theorem. But our last video says if you pick a really small region, and that's what we're doing here, we want a really small tetrahedron, what you're going to get here is our usual Green's theorem thing that looks like F2, Fx, minus F2, partial y, times the area of the bottom. What am I going to call the area of the bottom? Well, the triangle is the region, the T is the curves or the boundary. What I'm going to call the area of the bottom is A3, because it's perpendicular to K. I'm going to back up. C2 is the part that's actually perpendicular to J, so that's actually going to be on the left-hand side. And I want to calculate the work done by that. But if you're actually staying perpendicular to J, then the F2 part doesn't do any work. The only pieces that are actually doing any work are the F1 and the F3. And what we should be getting here is something like the partial of F3 with respect to y minus the partial of F2 with respect to x times the area of that triangle, which we're going to call A2 because it's perpendicular to J. And then the last part shouldn't be so bad. This is the part that's actually perpendicular to I. So we're calculating the work done by our 3D vector field, but along, I think, the backside. Yeah, that's the part perpendicular to I. But since you're perpendicular to I, the F1 doesn't do any part of the work. The only things that are doing the work are the F2 and the F3, and we talked about exactly how we wanted to do that. I think, if we do this right, let's see, the area should be A1, because that's actually perpendicular to I, and I want to make sure I write this down right. What am I doing? I'm doing F1. Let's see here. There's X, there's Y, there's Z. So this is going to be something like partial of F1 with respect to Z minus partial of F, 3 with respect to X. We will have a short way of actually remembering that. But this should be the work that's actually done by the vector field where J plays no part. This is going to be the work done by the vector field. Let's see here. No, this is where I plays no part, where J plays no part, and where K plays no part. And we get this great big, long, huge thing that this is the work done along a little tetrahedron. Now we have some simplifying to do in the next video, but that'll be for tomorrow. But the scary thing is, this whole thing's a dot product, yes, because it's something times something plus something times something plus something times something. Now, if you look at the first something, right, you're going to get a Green's theorem thing, a Green's theorem thing, and a Green's theorem thing, and those are the entries in the first column. And the first something, second something, and third something of the second vector are all areas. And so we're actually going to call that an area vector. And then we'll find out that that area vector is exactly the same thing as the area vector, what we normally call the area vector. Anyways, making progress. We now can calculate work done around a teeny tiny tetrahedron using things that look like Green's theorem.